Hello, my name is Willa Tobin, and I'm a senior in the Engineering Honors Program studying climate and space engineering with a concentration in meteorology. And today I will be presenting my capstone project titled Characterizing Spatial Relationships of the Interannual Variability of CMIP6 Carbon Flux Data. So to start off with some background on the carbon cycle. The primary mechanism of carbon exchange between the land and atmosphere are photosynthesis and respiration. Photosynthesis is the uptake of carbon by plants, and at the ecosystem scale is called gross primary production, or GPP. Once atmospheric CO2 is biologically fixed, it can be respired by plants, which is known as autotrophic respiration, or AR, or dead organic matter can be decomposed by bacteria and fungi in the soil, which is known as heterotrophic respiration, or HR. The net carbon flow into the land is defined as net biospheric productivity, or NBP. NBP is denoted by a double-headed arrow because it is highly spatially variable. We define NBP as positive when the net carbon flow is into the land and negative when the net carbon flow is into the atmosphere. In 2020, 31.6 petagrams of carbon dioxide was released into the atmosphere due to anthropogenic sources. About 50% of this is taken up by natural carbon sinks, and as a result, atmospheric CO2 levels increased by 2.6 parts per million from 2019 to 2020. The figure here is showing atmospheric carbon dioxide observations measured in Hawaii dating back to 1960. And as you can see, concentrations of CO2 in the atmosphere have been steadily increasing every year. NOAA reported 2020 as the second warmest year on record, with a temperature anomaly of 1 degree Celsius above the 20th century average. We know that greenhouse gases lead to warming surface temperatures, but recent studies have also shown that temperature anomalies are impacting the net carbon flux. Understanding the mechanisms controlling the net carbon land sink is becoming increasingly important as our environment is forced to adapt to growing levels of carbon dioxide in the atmosphere. The data used in our study comes from 5 Earth system models from the Coupled Model Intercomparison Project version 6, or CMIP6. The primary model used for our analysis is CESM2. Each CMIP6 model has slightly different parameterizations of Earth system processes, so we are using a set of 5 models to account for any uncertainty in model simulations. For each model, we analyzed the last 20 years of the historical simulation, from 1995 to 2015, to focus on characterizing recent trends. The terrestrial carbon cycle fluxes show large variations on seasonal timescales and regional spatial scales. Panel A shows NBP data from CESM2 for a polar, temperate, and tropical region with the long-term and seasonal trends removed to highlight the interannual variability of NBP for each region. Panel B shows the seasonality of temperature for each region. In this panel, we can see the summer peak of the polar and temperate region, whereas the tropical region does not exhibit a strong seasonal cycle. These seasonal patterns are mirrored in the average monthly NBP for each zonal region in Panel C. There have been multiple studies illustrating the dependence of the tropical carbon cycle on the interannual variability of temperature due to the response of carbon fluxes to temperature anomalies. Here we will expand this analysis to a polar and temperate region to characterize how temperature and the previously mentioned carbon fluxes are coupled. The data output from the historical simulations is globally gridded monthly data. For simplicity, we will only be using data from the Northern Hemisphere. We created 3 zonal regions to characterize polar, temperate, and tropical ecosystems and aggregated the data for each region at each time step to get one monthly value for each region. The latitude bounds for our 3 regions are 0 to 30 degrees for the tropical region in red, 30 to 60 degrees for the temperate region in green, and 60 to 90 degrees for the polar region in blue. The next step in our data processing was to remove the long-term and seasonal trends to get the interannual variability of each dataset. To illustrate this process, I am using the GPP data from the polar region. The long-term trend was removed by fitting a second-order polynomial to the data and subtracting it from the original dataset, as shown in the above figure with the gray dashed line representing the second-order fitting. When we subtract the long-term trend, we are centering the data around 0. GPP physically can't be negative, but for the purposes of our analysis, negative values are okay. The next component signal to deal with is the seasonal cycle. We removed the seasonal cycle from the detrended datasets by finding the monthly averages from 1995 to 2015. This figure shows each year's GPP cycle plotted in gray and the 20-year average plotted in blue. The blue cycle was then subtracted from each year. The light blue line here shows the detrended time series from the previous slide, and the dark blue line shows the new time series with the seasonal cycle removed. An issue we ran into is that is quite evident in this figure is that after removing the long-term and seasonal trends, most of the data for the winter months was clustered around 0. The majority of the data being around 0 for GPP, as shown here, underpredicts the relationship between GPP and temperature. The root of this problem comes from the model parameterizing vegetation to be dormant in the winter and therefore GPP and AR to be 0. We only want to consider months when the carbon cycle is active, so we defined a growing season as months with a zonal mean temperature of above 0 degrees Celsius and only considered data from those months. Removing the winter months from the data significantly increased the slope of the linear regression and highlights the stronger linear relationship between temperature and GPP for the polar region. We expanded this analysis to each variable pairing and region. For this presentation, I will be focusing on temperature and NBP relationships for each region. The polar region is temperature limited as ecosystems are dormant in the winter, so carbon exchange is restricted to the summer months. For every 1 degree Celsius increase in temperature, NBP increased by 0.37 petagrams of carbon per year, as seen in panel A. The positive couplings of each flux with temperature show that even when only considering the growing season months with the long-term and seasonal trends removed, temperature still exhibits controls over carbon exchange. For the polar region, GPP increased approximately twice as much for each 1 degree Celsius increase when compared to total respiration, which is why we see a positive correlation between temperature and NBP. The net carbon flux for the temperate region is less dependent on temperature than the polar region. For every 1 degree Celsius increase in temperature, NBP decreases by 0.15 petagrams of carbon per year, as seen in panel G. The sign of the correlation between temperature and the component carbon fluxes, which are GPP, HR, and AR, is the same as in the polar region, but the NBP temperature correlation becomes negative. This is due to the impact of temperature on HR increasing more than on GPP when compared to the polar region. There is a dramatic change in the impact of temperature on each carbon flux for the tropical region compared to the polar and temperate regions. For every 1 degree Celsius increase in temperature, NBP decreases by 0.66 petagrams of carbon per year. Increasing temperature now decreases the magnitude of each carbon flux. We speculate that this is because the mean temperature of the tropical region is close to the optimum temperature for photosynthesis, so increasing temperature will decrease plant productivity. Similar to the polar region, GPP decreases approximately double that of respiration for every 1 degree Celsius increase. When we bring in other models, we get a better sense of the validity of our results. 5 models is by no means an exhaustive list, but still gives us a range of values to provide some comparison. This figure condenses HR and AR into total respiration, or RT. The variable pairing is listed on the x-axis and correlation value on the y-axis. The models show the most agreement in correlation strength in the temperate region and the least agreement in the tropical region. Focusing on the first 3 columns, the models show modest positive correlations for the temperature and GPP and temperature and RT for the polar and temperate regions. The slope of the linear fit of the median model for each temperature correlation is used in the figure on the right. For the temperate region, the temperature and GPP and temperature and RT fits have similar magnitude slopes, shown in yellow and purple, respectively, in the right figure, which results in a net 0 correlation of NBP, shown in black in the right figure. The models show a larger spread in the polar and tropical region correlation magnitudes for temperature and GPP and temperature and RT, which result in a similar spread in magnitude for the temperature and NBP fit. For the polar and tropical regions, the temperature and NBP correlations do not spread around 0. The polar region temperature correlations for each model have similar magnitudes, indicating that for each model, the slope of the linear temperature and GPP fit is approximately double the slope of the linear temperature and RT fit. This is illustrated by the figure on the right with GPP median flux for the polar region of just under 1 petagram of carbon per year and the total respiration median flux of 0.5 petagrams of carbon per year. The same can be said for the tropical region, with the exception of the CAN ESM5 model due to the outlier temperature and RT correlation. Based on the relationships we have quantified, we can expect that a future warming scenario of 2 degrees Celsius would cause NBP to increase by 0.74 petagrams of carbon per year in the polar region NBP to decrease by 0.3 petagrams of carbon per year in the temperate region, and NBP to decrease by 1.32 petagrams of carbon per year in the tropical region. Overall, the biosphere of the higher latitudes is becoming more of a carbon sink. The opposite is true for the lower latitudes. Warming temperatures increase respiration faster than production, enhancing the carbon source of the tropical biosphere. Since the polar regions are warming faster than the tropics, we can expect to see more of a change in the net land sink of the poles compared to the increase in the net source of the tropics. Using modeled data presents some bias in our results, as each model has its own bias that influences our correlation values. We chose to use a model that showed results in the middle of the range to prevent overcorrelation of our variables. Our results also do not differentiate between correlation of the actual carbon fluxes and correlation between the mechanisms controlling the fluxes. Being able to quantify the relationship between these variables will allow us to improve our modeling of the carbon cycle. Observational data sets play a key role in this, as they provide a metric to compare model outputs to and provide accurate boundary and initial conditions from which to force the model. Carbon cycle fluxes cannot be directly measured at large spatial scales, which requires the use of models or upscaling methodologies. Our understanding of the dynamics at play for the interannual variability of the carbon cycle is limited, so quantifying how NBP, GPP, and RT are affected by each other and temperature will improve how we parameterize the carbon cycle in Earth system models and strengthen the quality of our future climate projections. Thank you so much for taking the time to listen to my presentation, and a special thanks to my advisor, Professor Gretchen Keppel-Alex, for supporting me and this project for the past 2 years. Some questions that I will now address in this pre-recording are, firstly, how did you get involved in this project? So I joined Professor Keppel-Alex's carbon cycle research team in the winter semester of my sophomore year. I was generally interested in the carbon cycle and wanted to learn more about how we model the carbon cycle. I was taking a course taught by Professor Keppel-Alex and reached out after class to talk more with her about her research and if there were any projects I could get involved in as an undergraduate. And so then here we are. And the next question is, what other paths could you have explored, or could other students and teams explore in the future on this project? So an aspect that could be explored further is how future warming will influence heterotrophic respiration of the high latitudes. A large reservoir of carbon is held in the frozen soils of the high latitudes, which is known as permafrost. And as temperatures rise and the permafrost layer diminishes due to the melting of the frozen layer, we can expect to see heterotrophic respiration increasing as that active soil layer is increasing. And a third question is, how do you hope to use what you learned from this project in your future career? So 3 of the main things that I learned from this project are a deeper knowledge and understanding of the carbon cycle. I learned data analysis and visualization techniques in Python, and I also learned a lot about technical communication. And so after I graduate from U of M, I will be working as a climate data scientist. And so all of these skills will be very useful in my future career. Again, thank you so much for your time. And that will be the end of my presentation.